Hi, everyone. My name is Laikh. This is Harry. We're super excited to share with you today about how NVIDIA Dynamo and TensorRT-LLM push the frontiers of scalable LLM inference. So today's trends for LLM applications demand that deployers stretch the limits of what was previously possible. Applications like document processing, video understanding, and code generation over entire repositories push the input lengths into the millions of tokens. At the same time, reasoning models and agentic workflows can dramatically extend output lengths. For scenarios requiring peak intelligence, we often see that only models with billions to trillions of parameters can actually achieve the quality that's required. And now, while all of these trends show increasing scale for deployment scenarios, deployers always want to serve more users with more interactive experiences. And given a myriad of constraints on hardware availability, power, and rack space, deployers are asked to find ways to do more with less. For these reasons, we built TensorRT-LLM. TensorRT-LLM is a framework that enables you to push the frontier of LLM inference performance on the NVIDIA platform. TensorRT-LLM is composed of a set of optimized kernels for common LLM inference operations, and a set of efficient runtime and algorithmic innovations that drive end-to-end performance. It's a combination of these powerful kernels and algorithmic runtime innovations that enable TensorRT-LLM to define and break through the frontier of LLM inference performance. TensorRT-LLM then packages these both up into a Pythonic framework that's designed for customization and extensibility. We recently released TensorRT-LLM 1.0, which marks a major update in the architecture behind TensorRT-LLM. The new architecture is built on PyTorch and designed to provide a seamless experience for both developers and deployers. With TensorRT-LLM 1.0, you can author models in native PyTorch for new model architectures, implement new innovative runtime features in a modular Python runtime, and iterate quickly for both development and deployment with an engineless eager execution model. TensorRT-LLM 1.0 is open source and developed on GitHub. So TensorRT-LLM's core goal is to push the frontier of LLM inference performance on the NVIDIA platform. And TensorRT-LLM has some of the best kernels for LLM inference operations, and these are actually widely used across the ecosystem, including in frameworks like vLLM and SGLang, and also in libraries like FlashInfer. But it's actually the combination of these powerful kernels with the open source runtime optimizations that enable TensorRT-LLM to both define and then break through the frontier of LLM inference performance. And so I'd like to discuss this combination and how it worked together today. So these charts here compare a single node performance between H200 and GB200 systems. So moving from the FP8 data type with Hopper to the FP4 data type with Blackwell can drive significant performance benefits. By quantizing to FP4, you can leverage 5th generation tensor cores on Blackwell to accelerate math operations. You can reduce the device memory footprint that boosts your production capacity of your system. And you can lower memory bandwidth pressure that helps during transfers to improve interactivity. Now, in addition to the hardware benefits of moving to FP4, we actually use a specific data type called NVFP4. This is a format that's designed for improved precision in number representation that enables you to retain model intelligence when quantizing to 4 bits. Now, this retention of accuracy actually enables you to design recipes that quantize more of your model into NVFP4, which in turn drives better performance. NVFP4 has 2 unique components that enable the format to have more precision in representation. So the first is that it applies fine-grained block scaling over 16-value blocks. And the second is that it uses an FP8 blockwise scaling factor, which trades off the range of representation for more precise scaling. So the small overhead of scaling smaller blocks more precisely enables better retention of accuracy, even while quantizing more of your model, and therefore the design of more performant recipes. Performant and quality-preserving recipes with NVFP4 are implemented in TensorRT Model Optimizer that generates a checkpoint that can be directly deployed with TensorRT-LLM. And we've published a number of these pre-quantized NVFP4 checkpoints for the most popular open source models and published them on Hugging Face at that link. Now, speculative decoding is another powerful technique that many know boosts the interactivity of your system. But in many modern LLM deployments, it can actually boost the production capacity across the entire frontier. So we're still comparing one node here of H200 with 8 GPUs and one node of GB200 with 4 GPUs. And when you layer on top speculative decoding with GB200, you can dramatically raise the max interactivity and the capacity at any given interactivity target. So while speculative decoding is also powerful on Hopper, the increased compute-to-memory bandwidth ratio of FP4 on GB200 makes Blackwell especially well-suited for this technique. So speculative decoding works by exploiting the typical memory bandwidth bottleneck that is observed during LLM inference by using spare compute to amortize the cost of loading weights onto the device. We have a fast but noisy draft model that's used to quickly generate guesses of what the next few output tokens of the full target model will be. And then the target model then verifies the token altogether as a batch, much like teacher forcing during training. All the results after the first incorrect draft token are discarded, and the first incorrect draft token is replaced with the corrected token from the target model. So this batch processing of guesses of these draft tokens means that if your draft model can typically generate good guesses, each forward pass of your target model can actually generate more than one token. Now with DeepSeek R1, the checkpoint provides a multi-token prediction, or MTP module. And this module can be either directly applied with speculative decoding, or it can be used autoregressively in a flavor of MTP that we call MTP Eagle. It's implemented in TensorRT-LLM, and it yields an even higher acceptance rate of the draft tokens. So all of the previous examples that we've talked about have been limited to inference on a single node. Traditional thinking goes that the best way to deploy an LLM is to take an LLM instance with as few GPUs as possible, and then you can scale the number of instances for best efficiency. The issue is that this kind of instance scaling won't directly improve your end-user interactivity or your per-GPU production capacity. As it turns out, with more advanced techniques for large-scale distribution, you can get even better performance results, driving both your max interactivity forward and the production capacity per GPU. So many modern LLMs adopt a sparse mixture of experts architecture. And a common approach to deploy these is to pack many experts into a single node. So this approach can be functional, but it's often suboptimal for system performance. Memory bandwidth bottlenecks when loading multiple experts onto the device and limited opportunities for per-expert parallelism both constrain your end-user interactivity in this scenario. You also end up with limited device memory capacity, which caps the number of concurrent users that your system can serve. So instead, you can choose to distribute your experts out across multiple nodes. The greater aggregate memory bandwidth in this scenario allows faster loading of experts from memory, and the greater number of GPUs allows for per-expert parallelism opportunities, which both improve your end-user interactivity. And then the increased free memory capacity per node enables your system to serve more concurrent users, in some cases scaling more than instance scaling would otherwise allow. Many developers today also use a technique called prefill decode disaggregation that drives efficiency in large-scale distributed deployments. So LLM inference is largely composed of two phases, a prefill phase and decode phase. And these two phases have very different characteristics. Whereas prefill is largely compute-bound, decode requires a little bit of compute, a little bit of memory bandwidth, and a little bit of inter-GPU bandwidth. And when you deploy a single configuration for both phases, it results in a system that's functional for both, but really optimal for neither. By disaggregating the configuration of these two phases, you can optimize for the requirements of both phases independently. So you can change things like the parallelism, the number of instances, or even the GPU type for each phase to tailor the kinds of optimizations. And that ultimately results in better overall system performance. Looking ahead, we're innovating in new ways to further specialize optimizations applied to different phases of inference. With prefill decode disaggregation, we separated the two coarse phases of LLM inference to allow for tailored optimization on each phase. But we can break down inference even further and apply specialized optimizations for the attention block and the FFN blocks or the MOE blocks of your model with a class of techniques called attention FFN disaggregation. We recently introduced a prototype of helix parallelism, which is a flavor of this attention FFN disaggregation in TensorRT-LLM. This technique enables efficient context processing for really long context lengths, think like over 1 million tokens. And it can have up to a 2x uplift in end-user interactivity in these kinds of scenarios. Unlike typical disaggregation, helix parallelism actually reconfigures the same pool of GPUs, which can help minimize operational overhead and complexity. With helix parallelism, we shard the KV cache across GPUs in combination with tensor parallelism during execution of the attention block. And this allows us to quickly process chunks of the context phase in parallel. And then we reuse those same GPUs that were used for KV parallelism during attention as a pure tensor parallelism during the execution of the FFN blocks. And so a prototype for this feature is fully open source and available on our GitHub now. So when it comes all together, the result of layering these techniques is a superlinear scaling of system production capacity at any given interactivity target, both with respect to the number of GPUs, and the superlinear scaling also persists even when you take in the increased cost between different GPU types. Now, unfortunately, there is no free lunch here. Each technique that we talked about brings its own trade-offs and its own costs and complexities to deploy. So for example, with wide expert parallelism, figuring out where to place each of the experts across nodes is critical for system performance. If all of the most popular experts end up on the same node, the benefits of wide expert parallelism are greatly diminished. TensorRT-LLM can help mitigate this risk by providing load balancers that analyze live traffic and redistribute experts with minimal overhead. But careful analysis may still be required to ensure an optimal distribution. With prefill decode disaggregation, orchestration of multiple instances across phases becomes a challenge, particularly when building a system that's tolerant to faulty nodes to maintain your service uptime. To discuss the opportunities of orchestrating and optimizing large-scale distributed inference, I'll hand it over to Harry to talk about NVIDIA Dynamo.
OK. Thank you, Laikh. My name is Harry, and I focus on inference serving at NVIDIA. Laikh just provided an excellent overview of the optimization capabilities of TensorRT-LLM. Now I'd like to shift the focus to the system level and introduce NVIDIA Dynamo, our core platform for system-level inference serving optimization. Dynamo is designed to provide robust foundation for crucial operations like scheduling, memory management, and data transfer. This foundation enables us to build powerful additional optimizations, including high-performance tokenizer, router, planner, and an advanced KV cache manager. Crucially, Dynamo is modular and is designed to support all major inference serving engines, including TensorRT-LLM, vLLM, and SGLang. Its components can be composed into a comprehensive solution or can be used standalone. So today, I'll provide a couple of concrete examples of how NVIDIA Dynamo extends an inference engine like TensorRT-LLM to deliver system-level optimization, focusing on our KV-aware routing and KV cache manager. I'll also share the details of several of the production-grade serving features that Dynamo offers. So let's first take a look at how Dynamo can apply system-level optimization with scheduling. Dynamo has a smart router capable of leveraging both KV cache hit rate and KV cache load. If the routing is purely based on capacity, in this case indicated by the KV cache load, a request can get routed to the top worker that has more capacity to process the request. But as you noticed at the bottom, the worker has the highest KV cache hit rate, and it would be better to route the request to the bottom worker even though it has the highest KV cache load. That way, we can start decoding tokens faster. We implemented a cost function that uses both KV cache hit rate and load to route the request for better performance. So using this KV-aware router from Dynamo, Base 10 was able to achieve an incredible boost in terms of both latency and throughput. The recent blog post highlighted 2 times faster time to first token, 1.5 faster time per output token, and 1.6x more throughput when serving Qwen3 480B coder. This is one way that Dynamo delivers system-level optimization in addition to performance from inference engines. Now let's take a look at Dynamo's KV cache management. Dynamo has KV block manager that enables developers to leverage all memory and storage available in the data center. This includes GPU HBM, host memory, local SSD, and network storage. By efficiently utilizing pre-computed KV cache across these tiers, Dynamo significantly improves latency. This approach leads directly to much faster time to first token because we avoid having to recompute the cache, allowing for immediate decoding. Furthermore, by leveraging multiple storage tiers beyond what can be stored in HBM, we can process significantly large context windows. This caching capability is especially attractive for use cases with high KV cache reuse, such as multi-turn conversations, code generation, or calling agents. Generative Recommender that leverages LLMs can also store large in-cache KV caches for their users to offer hyper-personalized recommendation. So Laikh previously talked about a powerful technique for improving throughput given latency called prefill decode disaggregated serving. With Dynamo's KV block manager, you can provide additional benefit on top of disaggregated serving. So as you can see, in this example on the right, we achieved 2 times faster time to first token for Qwen332B using KV cache offloading, even after applying disaggregated serving. So this opens up additional avenue for saving total cost of ownership because you can potentially reduce the number of GPUs used for prefill as pre-computed KV cache can instead be fetched from the KV block manager. Now we'll take a look at production-grade serving features from Dynamo. So beyond providing foundations for system-level optimization, we have a suite of features that can help to go from configuration to production. First, Dynamo provides developers an ability to find configuration for achieving best performance with disaggregated serving. It is really painstaking to come up with optimal parallelism settings for both prefill and decode stages, and make sure that it works with your GPU setup. With our offline configurator, you can generate an optimal config in less than 1 minute. It's blazingly faster than having to perform sweeps over several hours or days on expensive GPUs. After determining the best initial configurations, we can let Dynamo handle performance optimization in real time. This is super simple to set up. Users just need to specify the SLA they want to maintain for their workload. In this case, specifically for time to first token and time per output token. And Dynamo handles the rest. It can automatically scale prefill and decode workers based on real-time traffic. When you're scheduling these workers onto your GPU cluster and need to auto-scale them, you'll often run into many problems with efficiently deploying onto Kubernetes. Dynamo provides a sophisticated solution for scaling disaggregated serving workloads on Kubernetes with the ability to optimally schedule based on network topology. And after all this, you now have many components and microservices on your GPU cluster. And then the big question becomes, how do you actually make these workloads stay up and running no matter what may happen? And luckily, Dynamo has thought through many of these common challenges in LLM serving, and it tackles them right out of the box. So let's look at the offline performance configurator first. We have a tool called AI Configurator that is able to find the projected difference between aggregated and disaggregated serving. You can input your model, engine, SLAs, GPU cluster details, and it will show the estimated performance benefit in terms of throughput given latency. AI Configurator outputs the estimated performance parallel curve, as you see on the right. But it also shows you the top 5 configurations that gives you the best performance. And any of these configurations can be then deployed right away to Dynamo. And the biggest benefit of this tool is saving your valuable time and time on GPU. Performing this search will only take less than 1 minute on your laptop, and it does not require you to run the full configuration sweeps over the expensive GPUs. Right now, we support more than 30 popular models, such as DeepSeek R1 or Qwen family of models. This tool only supports TensorRT-LLM at the moment, but we are adding support for more models, as well as SGLang and vLLM. And we are doing this by collaborating with the Mooncake team. So far, we talked about how to determine initial best configurations with AI configurator. But in production serving, having the best initial configuration is not enough because the traffic patterns can fluctuate in real time. So we built a feature called Planner that tunes your inference deployment to the real-time traffic. Users simply need to provide their SLA in terms of time to first token and time per output tokens. And Dynamo Planner will take care of it automatically. So we'll automatically scale prefill and decode workers to improve the performance in real time. It's really that simple. Planner does this by first profiling the model offline, and then predicting the load and predicting the load from live traffic, and estimating the time to first token and time per output token to make an intelligent decision to scale prefill and decode up and down. We recently had our partner, Alibaba ACK team, announce performance benefits achieved with Planner at their Apsara conference. Alibaba ACK team was able to observe 80% reduction in time to first token while using 5% less allocated GPUs by testing Planner with their traffic. And you will recognize that AI configurator and Planner have a lot of synergy together. And we also thought the same way. And so we integrated AI configurator as part of offline profiling step with Planner. So you input your model, engine, GPU cluster, select your preferred configurations, and automatically deploy to Dynamo with Planner turned on. And it will continuously maintain your SLA. Using these two tools, you can find the best initial setup offline and automatically tune performance online. So we fixed the configuration problem for both online and offline use cases with AI configurator and Planner. But there's another big problem. Let's say that you have 3 prefill workers and 2 decode workers in your disaggregated serving setup. If you get a burst of requests and Planner decides to scale this up to 3 decode workers now, how do you optimally schedule this 3rd worker on your cluster so that it's in the same NVLink domain as the other workers? Today, when users deploy with Kubernetes using tools like leader worker set, prefill decode disaggregation cannot be scaled independently. So that means you can only scale prefill decode workers with fixed ratio in a pod group. The dynamic scaling or dynamic auto scaling for prefill and decode using Planner we saw earlier in the previous slide cannot be deployed in this fashion. It is also not aware of the network topology in our cluster, and therefore can't guarantee that you can schedule GPU resources in proximity. This is very crucial for disaggregated serving and also wide expert parallelism that Laikh has mentioned before. So we created a product called Grove that is able to gang schedule your workloads with topology awareness. Grove introduced pod click set for gang scheduling, so all the components can be scheduled simultaneously. And furthermore, by specifying scaling group for prefill and decode, they can be scaled independently and dynamically. And Grove is capable of processing topology hints to schedule workers in physical proximity. So with Grove, we were able to scale prefill decode disaggregation seamlessly. But there still is another problem. With Kubernetes, there is some guarantee that, with Kubernetes, there's some guarantee of fault tolerance, but LLM serving requires more granular fault tolerance. Dynamo has a suite of fault tolerance features for developers to reliably serve LLMs. So here are some highlights. We provide high availability for front end and router that shares the router state. When a router comes down, there's no downtime as the remaining routers can function with the shared router state. Dynamo also provides request cancellation which can automatically propagate through the components to save valuable computation. For example, if users cancel tool calling, having the request to proceed with constraint decoding and compiling it to generate structured output will add up significant amount of wasted compute. Dynamo can actively prevent this by offering cancellation throughout. Lastly, when a GPU dies, Dynamo is able to automatically migrate requests to healthy worker, ensuring fault-tolerant LLM serving. We have some tests on our GitHub that you can run if you want to test out these features for fault tolerance. If you want to test out the fault tolerance scenarios on a Dynamo deployment. So that concludes our talk on Dynamo and TensorRT-LLM. NVIDIA is hosting a lot of events during the PyTorch conference and also Open Source Week. To see the full list of events, please use the QR code on the screen to get directed to our events calendar. Additionally, if you are interested in Dynamo and TensorRT-LLM, please check out our GitHub pages noted here and give us a star. Thank you so much, everyone, and we hope that you get a lot of benefit using our open source products like Dynamo and TensorRT-LLM. Thank you.